forgotten. Okay, thanks for reminding me. All right, so fluid dynamics. So there are two good reviews. One is by Pavel Kovtun on fluid dynamics, and then a good review, about this Schwinger-Keldysh effective field theory formalism for hydrodynamics, which is the one by Paolo Glorioso and Honglu. Okay, and please do interrupt me if you have any questions and comments along the way. So we're going to talk about fluid dynamics. As I said, it's a very old subject. It's you can find it everywhere in atmosphere flow, in the flow of atmosphere along planets, in water, even in the quark gluon plasma. So this should be a picture of two heavy ion particles which interact. And for a very short time, all the quarks and gluons, they fall apart and they behave as a fluid. So even relativistic hydrodynamics is relevant for nowadays problems. So, but I don't see, sorry. Let me make this smaller. Okay, so, so hydrodynamics, what is hydrodynamics? So if we take a very small volume element over here in some fluid, and we look at what's inside. So inside there are many microscopic particles, which are all hovering around with their own velocities, and we consider perturbations in a system which are of wavelength L, which is much bigger of the mean free path of the particles. So the mean free path of the particles is the space spent between two different collisions of the microscopic particles. So if L is much bigger than this mean free path, we can neglect all the microscopic constituents inside this fluid element, and we can consider the fluid as a whole. So we can consider this whole volume element as a single fluid element. So hydrodynamics is as an effective theory. Is when you can consider all the perturbations which are much bigger than some microscopic time scales, and also for time. So therefore, what you have to do is you have these fluid elements which are interacting with one another, and you assign some, so each of these fluid elements is at local thermodynamic equilibrium. And and you can assign to each of these fluid elements the hydrodynamic variables, which can be the velocity field, the temperature, and say the chemical potential associated with particle number conservation. So instead of considering all the microscopic particles, you consider these macroscopic fluid elements which interact with one another. So therefore, what do? You write what are the equations of motion of this fluid. Yes, is there a question? No, I guess not. So the equations of hydrodynamics, you've seen them probably in your undergrad studies. Let's say they are the Euler equations, which are dynamical equations for the velocity field. There is the continuity equation. And let's say there is an energy conservation equation. You've seen these equations at least once in your lifetime. Okay. So these are equations. So remember, so the variables that we have chosen are the velocity field. So they are d of these variables, where d is the number of spatial dimensions. There is one temperature and one chemical potential. So there are d plus 2 variables. So we better have d plus 2 equations in order to have a closed set of equations to determine these variables. So we have a number of quantities here. So for example, P is the pressure, and we take it to be a function of T and mu. So we give it an equation of state. For example, then we have rho, which is taken to be the variation of the pressure with respect to the chemical potential. So this is the particle number density. Then we have epsilon, which is the energy density, which is related to the other quantities in this way. And the remaining quantity to define is this S, which is the entropy density, which can be defined also through the pressure. So now all the variables are defined in terms of this T and mu. So now we have an equation for D equations for V, and plus one equation for the particle number density, which is also expressed in terms of T and mu, and one equation for energy conservation. So we have D plus 2 equations. Okay, so this is the set of dynamical equations which can be used to determine the hydrodynamic variables. So one way of think of this equation is that they can be recast as conservation equation. So we can write all three of these equations. So all three of these equations as in a compact way. So where I is the index that labels spatial components, and mu is the index, it's a space-time index, so it labels space and time components. So where this would be momentum conservation. So the particle number current conservation and energy current conservation. Okay. So, but we have to, what we have to do is to provide how these currents, they are expressed in terms of the original hydrodynamical variables to make sense of these equations. So this would be conservation equations, but we need to provide constitutive relations. So this means that I need to tell you how, for example, J0 depends on the other quantities, and it's simply rho, the particle number density. Gi would be the particle number kind of flux. Epsilon 0 is the energy density together with the rest frame energy, which is this quantity here. Then we have the energy flux. And then we have the momentum and the momentum tensor. Okay. And now you can check that what I said is true. So for example, you can check that this equation is really D0 of this quantity here, so D0 of rho, plus the spatial derivative of this quantity here. And this would be the continuity equation. So we can recast the continuity equation as a conservation of a current, where the current is given in this row. And you can check the other equations too. And you'll have to use that, you can see that, for example, the conservation of energy current is equivalent to the conservation of an entropy current, where the entropy current is defined, where the zeroth component is the entropy density, and the spatial component is entropy density times the velocity field. I don't know why that happened. So what we learned so far is that hydrodynamics can be recast as an effective theory of conserved quantity. Okay. So in fact, we can see this heuristically. We can see that, for example, if we think about a non-conserved quantity, so if we think about equilibrium, and there is some non-conserved quantity which has some specific value. And we look at perturbations, long wavelength perturbations of this non-conserved quantity over some length scales. And these non-conserved quantities can locally equilibrate back to equilibrium in a relatively fast manner. But if we think about a conserved quantity, say energy, which is perturbed around the equilibrium, it cannot equilibrate locally, but it will have to transfer. It will have to equilibrate only through transport. Think about charge. So charge can only equilibrate through diffusion. So different charge will have to be transported from places where there is less charge to places where there is more charge to go back to equilibrium. So, and this happens on length scales, which are much larger. So, and therefore, if the length scales of the perturbations are very large, as I said, and the time scales of the perturbations are very large with respect to some mean free from respect to some microscopic scale, which would be the microscopic scale of equilibration of the non-conserved quantities, then we can think that the only quantities which are relevant for the problem are these conserved quantities. So this is the upshot of hydrodynamics. You retain only the conserved quantities in the game, and all the other quantities you forget. Okay? Okay. So you can add to the game dissipation. So dissipation entails into modifying a little bit your equations. So now you don't have anymore the Euler equation, but you have the Navier-Stokes equation, which is something like this. So it's still the same equation as before, like a dynamical equation for the velocity field. But in addition, there is a term here on the right-hand side, which is related to the viscosity tensor. So this viscosity tensor, I can write it, I can decompose it in this way, for example. So it's a bunch of derivatives of the velocity field in the spatial directions. And can be parameterized by two quantities, at least here, for this example. So this quantity eta and the quantity zeta, I think. So eta and zeta are the shear viscosity and bulk viscosity.
Natalia?
Yes?
Where are the indices in the last term in the first bracket?
Oh, yeah, thank you. Thank you. All right, so this eta and zeta are additional parameters that we have to input to the hydrodynamic theory, because they are not determined by hydrodynamic theory. They have to be determined by experiments or by a microscopic calculation, so from first principles. Knowing the microscopic theory, you could determine what are these parameters. But in the hydrodynamic theory, they're just parameters. And they represent how the fluid is transported. So for example, we can understand it in this way. So think about a fluid moving in a pipe, let's say, and think about that at some point you try to push a little bit with a piston, like one part of the fluid, something like this, and then you remove it. So one layer of the fluid will try to go a little bit faster than the other layers. So this will be like some y direction, and this will be some x direction. But it can't be the case that one layer will flow completely independently from all the other layers, because there are still some microscopic processes in which some of the particles, some of the microscopic particles are transferred around in such a way that layers of the fluid will interact with one another. And therefore, if you push and then leave the force from one layer of the fluid, it will drag the other layers of the fluid along. So this phenomenon is captured precisely by the dissipative effects. And in this case, in particular, by this shear viscosity term, because it represents the transfer of velocity in the transverse direction, which is captured by this tensor here. So this will capture the variations of the velocity in the direction which is transverse to the flow. So, and how much this fluid layers drag the other fluid elements, it will be captured by the strength of this coefficient here, by the shear viscosity. And for example, different values of the shear viscosity will tell you which fluid you have at hand. So for example, with respect to water, honey will drag all the elements better. So honey will have a higher shear viscosity than water, in which the fluid flow is much more independent from the other layers. Okay.
Isn't the last term in the multiplying the shear viscosity the same as the one with the bulk viscosity?
Yes, so
a convention.
Yeah. So it's a convention to subtract the trace from this term, so that you're only left with really the shear part. So you can call this quantity here the shear tensor. And this will be the expansion. So this coefficient here, the bulk viscosity, will capture like how dissipation happens along the direction of the flow. Okay. So dissipation can be introduced in this way via some transport. Is there another question?
Yes, may I ask a really stupid question?
Yeah.
Before we go. So can you explain in a couple of words, why do you call this thing dissipation? I thought the dissipation is a loss of something.
Yes, we will come back to this, I think, in the next page. Maybe if I will not be exhaustive, you can ask me again. Is that okay?
Sure, thanks.
Okay. All right. So before going to that, let me make another point, which is here in this expression here, I wrote these two terms. So this term here and this term here, but I could have written more terms on the right-hand side. And in fact, the reason that I chose to write only these terms that I wrote is that they are only one derivative terms which act on the velocity field. I could write here other derivatives. So maybe two derivatives which act on the velocity field, or three derivatives. I can go on and associate to each combination of independent tensors some coefficient, some transport coefficient. And in fact, this is what's done. The reasoning behind differentiating between these terms and these other terms is that remember, we are working in this effective field theory approach, where the perturbations are much larger than some mean-free path, and times are much larger than some microscopic scale. And therefore, you can think that if you have, again, let's say some temperature, so this will be the temperature at equilibrium, and this will be this out of equilibrium perturbation of the temperature. So locally, the temperature does depend on position in space, but the gradients, so how the velocity, how the temperature is changing, or I could write here also the velocity field, same thing. How the velocity and the temperature are changing is very small. So the gradients are small. And therefore, you take a derivative expansion, and this means that higher and higher order terms in here, which appear here, they will become more and more irrelevant. So this is the logic of an effective theory approach. So you can write more and more terms with more transport coefficient, but they will become less and less important with respect to the leading order terms. This is because of the assumption that you make in hydrodynamics. And so what happens with this, with the addition of this dissipation, is that the constitutive relations will change. So the ones that he wrote before. So this will be the relations that tell you how the currents are related to the hydrodynamic variables. So you will have the leading order piece, so which I denote with this Tij0, which is what I wrote in the previous page. So this will be this quantity here. But now you have also these additional terms, sigma ij minus z delta ij theta. And in principle, you can go on. And for example, for the current, particle number current, this will be like this. And here, I introduced another term, which is also a dissipative term, which is called the conductivity. Okay, and this VI is another combination of derivatives. So in particular, it's a combination of derivative of this chemical potential over temperature. Okay, and more equation for the zero component of the energy current, for the space component of the energy. So while the constitutive relations change, the equations of motion instead remain the same. So you can still call them like this. So there will be still conservation equations written of this form, and also the mu J from 0, etc. What changes is the constitutive relations. which are written in a derivative expansion. Okay? Okay, so going to the question raised, why do I talk about dissipation? It has to do with the local second law of thermodynamics. So in fact, remember before I told you that the energy conservation is equivalent to writing that there is a conserved entropy current. But now the entropy current is actually not conserved, and it acquires this form. And then something like this. So it depends on these coefficients which I introduced, and I call them dissipative transport coefficients. And they're dissipative precisely because they appear on this right-hand side of the entropy current non-conservation. So in a sense, they create entropy. So the local second law of thermodynamics, as opposed to the global second law, where entropy is conserved everywhere. So the local second law of thermodynamics has to do with the local, the entropy has to grow like in the whole space-time. The local second law has to do with the small volume element. So it tells you that there exists an entropy current such that at equilibrium, it can be written in the form that I wrote before. So as mu, we have that S0 is the entropy density, and Si is entropy density times the velocity. And out of equilibrium, so when all these derivative terms are introduced, the local entropy current, the divergence of it should increase. So this means that there is a flow equation for the entropy, which is increasing. So in a small volume of element, in small volume of the fluid, entropy will increase and the flux will not compensate as it's usually in a continuity equation. So this fact that the entropy current is increasing locally, and the fact that at equilibrium you can write it in this way, this is the content of the local second law of thermodynamics. And we have to require compatibility with the local second law. So this means that we have to require that these coefficients over here, because these are structures which are positive semi-definite anyways, because they are squares of spatial quantities, we'll have to require that the shear viscosity is positive semi-definite, the bulk viscosity is positive semi-definite, and the conductivity is positive semi-definite. So these are certain constraints which are imposed on the hydrodynamic transport by the local second law of thermodynamics. And these particular coefficients, they are dissipative precisely because they create entropy. And if you go at higher order, so there will be other transport coefficients. So higher ordering derivative. This constraint coming from the second law will imply that certain coefficients are going to be equal to 0. So the upshot is that compatibility with the second law of thermodynamics will restrict the amount of possible transport. And you have to require that motion is compatible with this second law of thermodynamics. Okay? All right. I hope this was answering the question. Okay, so one other important topic is within this fluid dynamics is correlation functions. So presently, what like in experiments, if you want to consider like quark gluon plasma, which is created in experiments in CERN, what you observe is that there are some outgoing particles, and which are collected in this by the experiments, and what you measure are correlation functions. So you want to understand how are the correlation functions, what are the correlation functions. What it's measured are the correlation functions, and in order to say that the quark gluon plasma behaves like a fluid dynamical plasma, the correlation functions need to be compatible with the correlation functions of hydrodynamics. So what kind of correlation functions can you extract from the formalism that I just showed? So it's possible to show that constitutive relations plus these equations of motion will allow you to extract correlation functions. And let's illustrate this, this with an example. So the example is relativistic neutral hydrodynamics. You might imagine that the equation that describes this system, it's a conservation of the stress energy tensor, which from the non-relativistic equations that I had before, it's like unifying this momentum conservation with the energy conservation in a single object because of Lorentz invariance. So you have this type of equation. And constitutive relations means that you have to tell me how this quantity, the stress energy tensor, is related to the relativistic hydrodynamic variables. So in this problem, it is convenient to introduce sources. So that means that you are coupling your system to some background. And in this case, the source for the stress energy tensor is the metric. And the equation, this equation here, in the presence of the sources becomes the covariant conservation of the stress energy tensor. And as I said, the constitutive relation is about telling you how the stress tensor is related to the hydrodynamic variables, which in this neutral relativistic case will be just the temperature and the velocity field, which is now a 4 velocity. So this is gamma V, and u mu is equal to -1. So it still has d independent components, where d is the number of spatial dimension. And in the presence of sources, this quantity will also depend on the sources explicitly. So we know from linear response theory that the one-point function of certain operators in the presence of sources can be written as a as a retarded effect through this retarded correlation function. So you have a source which is turned on adiabatically, and then it's removed. And this source will create a perturbation, which is represented by this retarded correlation. So the one-point function will be different from its zero source value only after the perturbation is turned on. So this retarded Green's function, in fact, it's written using the Heaviside theta function, which tells you that, in fact, it's relevant for after the perturbation is turned on. And it's a particular combination of these operators. So it's the antisymmetric combination of these operators. So by using this linear response theory result, we can think of our stress tensor here as being a one-point function in the presence of the source, which is given by the metric. And therefore, we can extract the corresponding correlation function. Okay. So in our case, this would be something like this, schematically, G retarded times a perturbation, which I can write as H mu. H mu is the perturbation around the Minkowski vacuum. Okay. So we can determine the retarded correlation function. So two-point function of stress tensor by taking the derivative of the one-point function for the stress tensor that we wrote over here. With respect to the metric perturbation, and then at the end of the game, setting all the sources to 0. Okay. And this will be the retarded correlation function for stress tensors. Now, the point that I want to make is that, so this means that the hydrodynamics equations, in particular the constitutive relations, they contain information about the retarded Green's functions. And you can go further because you can look at nonlinear response functions. And in that case, you have the one-point function, which is given by the retarded correlation function, this two-point function of operators with one source turned on. But you can add more terms. You can have these additional terms which contain non-linear response. With some other retarded Green's function. So where this object here is now a three-point function, which now is schematically denoted by 1, 2, 3, where each one of these represents the value of the space-time coordinates, 1. And it's a combination of these Heaviside functions. So each of these is 2 of T1 minus T2. So it's a schematic notation. And it's some specific combination of nested antisymmetric correlators. Okay. So this means that from hydrodynamics, knows about retarded type correlation functions. So these ones, so this one here, this one here, which is given explicitly here, and more that follow. In principle, you can continue this expansion to have more nonlinear effects, and they will all be of similar form to this correlation function, some nested anti-commutator of operators. But it doesn't know about other correlation functions. For example, it does not know about the symmetric correlation function, about the symmetric two-point function, which can be written in this way, which is like the symmetric combination of these operators. Okay, so now for two-point functions.
Natalia, you're almost out of time for this session.
Yes, so I'll finish this discourse and then I'll stop.
Yeah.
So for two-point function, you're not such in a big worry because you can use the fluctuation dissipation theorem which is basically a relation between different correlators and how to analytically continue certain correlators, like an analytic relation between correlators. For example, for two-point functions, where you have the retarded correlator, the advanced correlator, which you can think of the time reversal of the retarded correlator, and the symmetric correlator, they are all related. And in particular, there is this relation here. The symmetric correlator can be obtained, so written in a Fourier space, can be obtained from the retarded correlator. So the imaginary part of the retarded correlator multiplied by this cotangent of omega, the frequency, over 2, the temperature, is going to give you the symmetric correlator. But for higher point functions, similar theorems exist. So similar generalized FDT theorems. But you will not be able to get all the correlators from just the retarded Green's functions that you get from hydrodynamics. So from these correlators here, so from particular from these ones which appear at nonlinear order, you can get some of the symmetric correlation functions, which will be similar to this one, where the anti-commutator, let's say, is replaced with the commutator. Sorry, where the commutator is replaced with the anti-commutator, but you will not be able to get all of the correlation function. So this is a little bit of a drawback. So hydrodynamics is not encoding all the correlation functions when you go at higher order in the nonlinear response theory. Okay, so I'll stop here. I have one more thing to tell you, but I'll tell you later. So for the moment, I'll leave you with a summary slide. Okay, and I'll pause the recording too.
Are there any questions?
Okay. So there was one last thing that I wanted to say about the topic of fluid dynamics, which has to do with stochastic hydrodynamics. So stochastic hydrodynamics, so we have seen before, like in this example of layer of fluids, that there can be transfer of microscopic particles from one layer to the other, and this is incorporated by the diffusive terms in the constitutive relations. So this would be microscopic particles. But there could be also, we also have hydrodynamic perturbations themselves. And if the wavelength of the hydrodynamic perturbation themselves is smaller than these typical scales of where variations occur, there could be a transfer of hydrodynamic modes as well between these different layers. So this happens even at equilibrium. So at equilibrium, you can think that there are still some statistical fluctuations which can still modify a little bit, which happen above equilibrium. So this means that if we have some transport coefficients, actually what we have defined to be the shear viscosity and the bulk viscosity and the conductivity, these are only bare transport coefficients. And they need to be corrected by this fluctuation, by the presence of fluctuations. So we can illustrate this problem with a simple example, which is the Langevin equation. Which is an equation of this form. Where you have some deterministic terms, like this one and this one, and then you have a dissipative term. So this nu is related to dissipation, because this nu is associated with only one derivative with respect to time. So this x is some variable which is depending on time. And this psi is an external force, a noise term, an external random force. So you can understand this equation as mimicking the Brownian motion of a particle in a fluid. So the small particle in a fluid will feel the fluctuations of all the other particles in which it is immersed, and it will move because of the fluctuations of the system. So this noise term here is to incorporate that effect. And you have to provide how this noise is distributed. So it's common in this phenomenological approach to assume that this random force has a Gaussian probability distribution. So it's a white Gaussian noise. And therefore, it's like this, and the correlation is of this form. And the reason you pick particularly this coefficient, so precisely this nu, which is related to the dissipative term, comes from requiring that the dynamics is consistent with the fluctuation dissipation theory. So both this, and these, they are requirements which are imposed by hand. So when you deal with stochastic hydrodynamics, you will do the same. You will write your equations of your constitutive relations and your equations of motion, and you add additional noise terms. And specifying a specific stochastic hydrodynamics is about telling what is the noise term, what is the coupling to the other hydrodynamic variables, and how it is distributed. And the correlation functions now can be computed by looking at this type of path integral, where you have to impose the equations of motion. So you have to impose that the dynamics is compatible with the Langevin equation. So this delta function imposes the equation of motion. And then you have an exponential, which tells you that you are averaging over the noise. And the noise has a specific distribution, which we have just specified, and it's compatible with writing it as this Gaussian term, psi square. In particular, you can lift up this delta function in the exponential by introducing an additional variable x tilde, and you will have something of this form. T and x dot dot nu x dot plus cx minus xi x tilde, and here we had xx, and this will be this exponential term. Okay. But, and this is how you would obtain the correlation functions in the presence of noise terms. So you will have to average also with respect to the noise variables, which are chosen to be specifically with some certain specific distribution and certain coupling to the equations. But all of this is clearly phenomenological. So a systematic treatment of fluctuations is needed. Okay, so I hope I convinced you that there are like a couple of drawbacks of this formulation of hydrodynamics that I presented. So one is this, so the inability a little bit to incorporate systematically stochastic fluctuations. And the other one was this point where hydrodynamics is not incorporating all the correlation functions in the game. So in fact, so now that I have described for you fluid dynamics, let me give you, before jumping directly in the Schwinger-Keldysh formalism, a little bit of motivation for the topic, which is as follows. Because of these drawbacks, what is needed is an effective field theory formulation of hydrodynamics. So a more modern formulation of hydrodynamics, which is based on an action principle like we are used to in quantum field theory. So with modern techniques, where hydrodynamics comes from an effective action. So the equations will come from a variation of principles. So we wanted to write as a modern, in an effective field theory language. So this means that we have in the UV, for example, we have a partition function which depends on sources. So this will be some sources. This will be some microscopic fields. And It should be some microscopic action of fields coupled to sources. And we imagine to integrate out all the heavy fields, and we are left with some low energy degrees of freedom, and obtain an effective action of low energy degrees of freedom coupled to sources, so in the infrared. So what we want is to identify what is this object in the case of hydrodynamics, and then play the game of conventional effective field theory. So merely identifying what are the degrees of freedom, so the degrees of freedom for hydrodynamics, and then impose symmetries on this effective action, and construct what is the most general effective action that is compatible with these requirements in the case of hydrodynamics. And this approach possibly is more general than what I described before, because what I described before is just based on equations for hydrodynamics. And this is a little bit, like from a theorist point of view, is more pleasing to have an action principle from which all the equations follow. And this approach, trying to understand hydrodynamics from an effective field theory, is also something which started at least in 1911. And some progress has been made in this century, but the main obstacle has been always how to include dissipation. So the dissipative effects. So let's illustrate this problem with an example. Again, we have this Langevin type equation. Where here I'm not including the noise term. So if you want to write this equation from the point of a Lagrangian, how would that look like? So, well, I can think something like this. Something similar to the Lagrangian for a harmonic oscillator. But what happens when I want to write this first derivative term? Is it something like this? If you think a little bit about this, you can realize that this is actually a total derivative term. So you cannot really write it like this. So you cannot really write a term of this form from a Lagrangian point of view using just these variables here. So this approach will not work. What works instead is writing a Lagrangian of this form. But actually now I cheat a little bit and I introduce an extra degree of freedom x tilde. And therefore, which plays, it's like a Lagrange multiplier. Then the variation with respect to x tilde will imply the equation of motion that I wanted to implement at the level of an effect, of an action. And which is also what I wrote before in the stochastic case. Remember, like, look at this equation here. So I want to motivate for you that because of this additional degree of freedom, I have to think about a different type of an effective action here. So instead of this one, I will have, instead of this one, we will have an effective action which contains two types of degrees of freedom in the infrared effective action. And this can come from a Schwinger-Keldysh path integral approach. So hydrodynamics, we will be able to write it as an effective field theory if we are considering Schwinger-Keldysh effective field theories. So this approach has been very recently performed. around 2015. And let's say the main contributors was Ongliu and Paolo Glorioso, and on the other hand was Rangamani, Loganayagam, and Hael. And I also contributed myself to the subject with Amos Yarom and Christian Jensen around 2017. So the breakthrough of writing an effective action for hydrodynamics in the presence of dissipation was to use a Schwinger-Keldysh path integral. So this will be the modern approach. That includes dissipation. And it will also include fluctuations. As we will see. And it will provide all the constraints that on hydrodynamics. So those constraints which are coming from the entropy current from the second law of thermodynamics, and more constraints which from a phenomenological point of view could have not been guessed. Because from a phenomenological point of view, you can go, okay, I have to impose compatibility with second law, some other things like Gonzaga relations, but where do I stop? From this point of view, like having an effective action and all the symmetries, all the constraints should be implemented at this level. Okay. So before going into like the complete Schwinger-Keldysh effective field theory formalism, let me introduce the Schwinger-Keldysh formalism itself. So fluid dynamics is about systems which are out of equilibrium, and it incorporates correlation functions, thermal correlation functions. So they are retarded type correlation functions, but they are thermal. So we are interested in correlation functions in a mixed state. So a mixed state is represented by a density matrix, which is defined, let's say, at some time t equal minus infinity. And we have to think about this like a Bryan cat. So therefore, its evolution, so the state at the same time t will be given by an evolution of the state and an anti-evolution. So there is a U and U dagger, which are acting on the Bryan cat of the density matrix. So if I want to, you can represent this pictorially by saying that there is a density matrix in the infinite past, and there is a leg of evolution forward to the infinite to some time t, and then a leg of backwards evolution back to where the initial state is defined. So if you want to compute one-point functions in this state, you can define it this way. And you can now associate the time dependence from the operator to the density matrix. And you can write it explicitly like this. So this would be the trace of the operator, and then we write this expression here into here. So this will be u of t minus infinity rho, and then this U dagger. Okay, so pictorially taking the trace, it's like considering this situation instead, where you have the state defined in the infinite past, evolution forward to time t, and then you kind of like glue these pieces together and you evolve backwards to where the state is defined. And here is where you have inserted the operator, let's say. And one thing that we should notice is that we can always insert, because this U is the evolution operator, it's a unitary operator, we can always insert in any point the identity, which is equal to ut plus infinity, and the anti-evolution, u plus infinity t. So I will insert it here, u t plus infinity, u plus infinity t. And then we have this operator, u t minus infinity, rho minus infinity, and u dagger t minus infinity. So pictorially, this means that we can take this evolution and past the point of insertion of the operator, we can always extend this contour all the way forward to infinity. So this will be this part of the evolution, and then backwards here, and then back to where the initial state is defined. Okay, so this will be t equal to plus infinity. And for thermal states, the density matrix has a specific form, and it can be seen as an evolution in imaginary time. So therefore, this contour for the thermal state will look like this. There is a forward and backwards evolution from minus infinity to plus infinity in real time. And then there is another evolution in imaginary time, where these two endpoints are identified with one another. After a period B, which is specified by this parameter here, which is also related to the temperature of the initial state. Okay? Okay. And so I talked about one-point functions, but you can also look at generic correlation functions. Generic correlation functions of the form, for example, of 4, 3, 2, or 1 in the same state. So where again 4, 3, and 4, this is to mean that it's time with the label 4. So this will be written like this. So trace of, and I start from defining the density matrix, which is where the initial state is defined here. And I evolve it forward to where the first operator is defined, somewhere over here. Then I evolve it further to the second operator, then I evolve it forward, but let's say that the time at which the operator 3 is defined is somewhere smaller than the time at which the operator 2 is defined. And then there is another evolution of 3, which say it's somewhere over here. And then the evolution backwards to where the initial state is defined. Okay. So this contour here, we can also, as with the previous arguments, we can always insert additional evolutions as long as they are past the last insertion of the operator. So we can insert them here, here, and here. And actually this contour would be equivalent to this one, therefore. Or this is t equal to plus infinity. And then backwards to where the initial state is defined. So this is an example of an out-of-time ordered correlator. Where we have chosen T1 to be smaller than T3, to be smaller than T2, to be smaller than T4. Okay. So one specific class of correlators is the one which is given by Schwinger-Keldysh contour. So in particular, let's take the figure of before and consider, instead of the times that I chosen before, let's consider the case where the operators are inserted in this way. Three. But now O4 is inserted somewhere here. So we are choosing this particular configuration. T4 is more than T1, T3, and then T2. So we can always move this operator here by using, again, the properties of the unitarity of evolution. We can move it over here. So we can actually rewrite this correlation, this contour, in this way. Because we can eliminate all the additional evolutions and anti-evolutions which don't contain operators. So this particular two-folded contour, where there is only one evolution forwards and one evolution backwards, is what I call the Schwinger-Keldysh contour. And the correlation functions which are defined on the Schwinger-Keldysh contour, they are of a specific form. They will be defined as path ordered over the contour itself. So the correlation functions will be of this form. There will be time ordered for the operators which are in the upper half of the contour. and anti-time ordered for the operators which are in the lower part of the contour. This is because when we have an evolution and operators given in one single evolution, the correlation functions that you get from that contour, it's usually the Feynman correlator. So it will be the time-ordered correlator, will be this part. And because in the lower leg there is an anti-evolution, you will get the anti-Feynman correlator, so this anti-evolution part. And you can write this conveniently by saying that you take a path-ordered sorry. You take a path-ordered correlation function in which you assign to all the operators which are in the upper part of the contours, you assign a label 1, and all the operators which are in the lower part of the contour, you assign a label 2, like I did here. So the path ordered is precisely telling that whenever the operators are in the upper leg, you'll have to take the time-ordered correlator of them. And then you have to insert to the right of the time-ordered correlators, the correlators which are in the lower part of the contour, and to those you have to assign the anti-time ordering. So this particular set of correlators is at the Schwinger-Keldysh correlation functions or time-ordered correlation functions, let's say, in a generalized sense. Okay. Okay, so these type of contours are central to our discussion. So these Schwinger-Keldysh type contours and Schwinger-Keldysh type operators. So we want a more formal way of defining these correlation functions and contours. And for that, we can say that they can be derived from a Schwinger-Keldysh path integral. So, and I write the Schwinger-Keldysh path integral like this. So it's now the trace of the evolution operator and the anti-evolution operator over some initial state density matrix. And this evolution operator and anti-evolution operator, they are taken with respect to different sources. So these A1 and A2 are sources. And you can associate a different source to each leg of the contour. In particular, for example, for the microscopic representation or the field theory representation of this path integral, what you have is a double copy of the microscopic field microscopic effective action. And the double copy is taken with this minus sign. And this minus sign here is precisely to mimic the fact that the second copy is in an anti-evolution leg. And the sources are obtained by coupling certain operators. Say operator 1, which is made of microscopic fields 1 with source A1. And then operators in the lower leg, 2 by 2, coupled to source 2. And there is also a boundary condition in which the fields and the sources are identified at future infinity. Okay. So now we can define the Schwinger-Keldysh correlators by simply taking the variations of this path integral, of the Schwinger-Keldysh path integral, with respect to the sources. So for example, you can define, so these correlators being 1, 1, 2, 1, etc. So at time t1, t2, t3. And in particular, if we want the connected correlation functions, we will have to take this generating function, the connected generating function, and we take the variation with respect to source 1, following this pattern, source 1, then source 2 at time 3, etc. And this is precisely the path ordered so 1, T1, T2, T2, so 1, O1, T2, O2, T3, etc. And this is -1 to the power of m, where m is the number of in the lower leg. So you will get a minus sign because of this minus sign over here and this minus sign over here. Okay, so with these very long expressions, we can make an example, which is the example of two-point functions. So for example, we can compute what is G11. So this will be the derivative 2 times. And then we have to set the sources to 0. So n equal to 0. So because both of these sources are associated to operators inserted in the upper leg, because they have this index 1, which refers to the upper leg, we said that when the operators are in the upper leg, so this will be defined as the path ordered correlation function of the operators O1 and O1. Because they are both inserted in the upper leg, you will have to take the time ordered correlation functions of those. Which is simply given by theta 1, 2, or T1, T2. Okay. And you can derive similar expressions for these operators here, for these correlation functions here. So you will get here the Weidmann function. Here you will get this Weidmann function. And here you will get the anti-time ordered correlation function. Okay. So this sounds a little bit abstract, but we can make a very good connection with what we were saying in the first hour if we go to another basis, which is the Schwinger-Keldysh basis. The Schwinger-Keldysh basis, you define the average fields and average operators. So the average sources and the average operators. And therefore you see that the coupling between this will acquire a plus sign. And the operator in A will become an operator in the difference operator will be coupled to the average source, and the average operator will be coupled to the difference source. So the correlation functions in this basis are of this form, which are the path ordered correlation functions of this type of operators, which can be obtained by variations of the corresponding sources, and then setting the sources to 0. So, for example, a very simple example is this one. So consider GRA at 2 different times, 1 and 2. So this will be the path ordered of OR of 1, OA of 2, where OR is the average at the same time, and this one here is the difference between the 2 operators. Okay, so you will have, when you multiply this term with this one, they are all both inserted in the upper part of the contour. So you will have a time ordered correlation function. When you multiply this one with this one, because one is inserted in the upper part and one is inserted in the lower part, you will have to put the one inserted in the lower part first and the one inserted in the upper leg second. And multiplying this one with this one, you will get the opposite. And then multiplying this one here with this one, you will get the anti-time ordered correlation function. O1, O2. Okay. Now, if you write this explicitly with respect to using the Heaviside step functions, you will get something of this form. So for this thing here, you will get θ1, 2 of operator 1, operator 2, plus θ2, 1, operator 2, operator 1. So then this one is unchanged, but I can insert an identity which is theta 1, 2 plus theta 2, 1 equal to 1. So I will rewrite this term as this, minus theta 2, 1, O 2, O 1. And I will do the same for this term. And then I write this term explicitly, which is minus theta 2, 1, O 1, O 2, minus theta 1, 2, theta 1, O 2. Okay. So now you can see that there are some cancellations. So this term here will cancel with this term here. And then this term here will cancel with this term here. And you're left with this term here, which is equal to this one. So it will sum to give to get rid of this 1/2. And then this one, this term here is equal to this one here. So eventually you reproduce this correlation function here. So because of this minus sign, you get O1, O2, the antisymmetric combination. And guess what? This is equal to minus IG retard Green's function. So GRA is the retard Green's function. Then equivalently, you can prove that GAR is equal to minus E, the advanced Green's function, and GRR is the symmetric Green's function, and GIA is equal to 0. So this was to tell you that all, and you can like do this as an exercise. This is to tell you that all the correlation functions, the symmetric retarded correlation functions, are incorporated in this formalism. And I gave you like the example of 2-point functions, but you can do the same for higher point functions. So you have already a hint that this formalism will work into incorporating more than hydrodynamics, the usual hydrodynamics tells you. It incorporates all these additional correlation functions. Okay, so I think I'm out of time, but I have like important things to say. Mm. So I don't know what I can do or what I should do. Can I maybe take like the discussion is in 10 minutes?
Yeah, the discussion is at 4. Mm-hmm. Or maybe how much time do you need to finish this lecture, let's say?
Actually, maybe like 10 minutes. So maybe like at 4 I can take 10 minutes then?
Yeah, I was thinking the same.
Yeah, thanks a lot.
Yeah, let's do that then. Let's make a small break, and then at 4 you take 10 minutes and we continue with the discussion.
So I'll leave the summary page for the moment.
Yeah, so in that case, maybe we wait for the questions till you finish this part, and so everybody can make them at the end of the whole lecture.
Yeah, that's right.
So yeah, so let's take a break now, and we resume at 4.
Okay.